All right, without any further ado, I would like to introduce Charles Papin, who is the main developer behind SpinalHDL, a hardware description language which you can use to program FPGAs and the like. He is working on SpinalHDL full-time, and I'm looking forward to the presentation. Please give a warm round of applause for Charles.
Thank you. So during this talk, I will start to tell you a little bit about why VHDL and Verilog are not so good. Then I will introduce you SpinalHDL, and all the rest of the presentation will be about showing you example and thinking about why this is better by the way the examples are done. So yeah, as I said before, this presentation will only be about synthesizable hardware. I will not talk about any simulation features or this kind of things. So yeah, VHDL and Verilog were initially designed for simulation and documentation purpose, and it's only later that they were adopted as an input language for synthesis tool. And that was a very long time ago, which means, yeah, VHDL and Verilog miss many features that could be interesting. And to infer hardware, you have to use simulation constructs like process and always block, which doesn't really make any sense from an RTL point of view. Although you don't have things like object-oriented programming and functional programming, it could seem strange to talk about object-oriented for synthesizable hardware, but in fact, it makes a lot of sense. And I will show you some example where it is really powerful. Then, in VHDL and Verilog, simple concepts are often very verbose, like instantiating a subcomponent or a submodule is very painful. Although you don't have some notion of interface, you are always enumerating signals one by one, and many other things that make them not so good, and you don't have possibilities to rise the abstraction level. If you use VHDL and Verilog, you will be still stuck in kind of wire abstraction layer. You will still have to connect everything by hand. You will still have to define gates one by one. I mean, it could be better. Then there is VHDL 2008 and System Verilog, but yeah, they are not really there to save us. I mean, they still keep the same wrong paradigm to infer RTL. You still have to use simulation constructs. You are still using the event-driven paradigm to infer the RTL. Then they still didn't offer any meta-hardware description capabilities. And the idea tool support could be very bad. I mean, there is many interesting features in those both language, but depending the idea tools that you have to use for simulation or for synthesis, you will not be able to use them, which means, yeah, you are still stuck in a subset of them. And also, as instance, System Verilog wrap a very interesting features, which is interface definitions. But we will see in this talk that even this features is not that good with System Verilog. So yeah, what to do next? My solution, and it's a solution of other people. One solution is to use VHDL and Verilog as netlist language, which are automatically generated from a higher level language. And there I go with SpinalHDL. So basically, it is an open source project that I started in December 2014. It's focused exclusively on RTL description. So the idea behind that is to not do any compromise, to really have the best language possible to do one very precise thing, which is describing RTL. Then, since the beginning, it was seen to be interoperable with existing tools, because you can go to the Xilinx company and ask them to support your brand new language. They will never do that. So the SpinalHDL compiler is able to generate its output netlist as Verilog or as VHDL. You can also integrate legacy IPs inside the SpinalHDL hierarchy by using a black boxing system. It's a little bit like having a C header file. Then his abstraction level starts at the same level than VHDL and Verilog, or nearly the same level. But the thing is, on the top of SpinalHDL, you can build new abstraction level. you can build new tools, and it is its biggest powerful side. Then there is the flow. So basically, you will have to define your digital order description by using .scala files in SpinalHDL. Then you will ask the SpinalHDL tool to generate the corresponding VHDL or Verilog netlist. Then you can grab your VHDL or Verilog IPs and put them all together. And you can use your flow as before by using same simulation tools than before and same synthesis tool than before. So yeah, now I will start with some examples. So just some things, last points to talk you. So SpinalHDL will not create any overhead in the generated RTL. You will not lose gates, you will not lose performance because it is not kind of HLS tools. You know, for example, there is Vivado HLS where you write some, not arbitrary, but you can write some C algorithms that will be translated automatically into RTL. So SpinalHDL is not that. SpinalHDL is really an RTL approach where you will have to define register a little bit as before and gates a little bit as before. Then all components hierarchy and all signal names that you define in SpinalHDL are preserved in the generated RTL, which means you can do your simulation as before with the wave. You can look signals and match them with your SpinalHDL description. It's not an issue at all. And OK, SpinalHDL, in fact, is not really a language. It's what we call an internal DSL. So SpinalHDL is basically a Scala, which is it is a Scala library. So Scala is a general purpose language, and SpinalHDL is a library implemented on the top of it. And it could seem strange to have some language into another one, but in fact, this is probably one of the best part of SpinalHDL. So, example. Yeah, there is a simple example where you have some common conditions to drive a mux, to drive a counter, to drive another counter with a reset value. In VHDL, you will have to, if you want to do that, you will have to write 3 different processes because you are in an event-driven paradigm, and yeah, this is how you have to do things. It is really boring, it is really variables, and as you can see here, you duplicate 3 times the same condition, which is not very good in terms of code quality. And there is equivalence in SpinalHDL. So first, to define signals, it's already different than if you want to define this combinatorial signals, you just say, I want a bool, which is a hardware Boolean data type. Then if you want this register, you say, I want a reg of this given data type, which is an unsigned of 4 bits. So it's not like in VHDL and Verilog where a signals become a register because you assign it in a clock process. So it's not that. Here, it's really explicit at definition. And this simple fact changed a lot of things. Like, for example, you can assign all those guys inside the same if condition. So it is a random example, but basically, it happens very often, like in a state machine where you have a combinatorial path and a sequential part. You have to duplicate switch statements, and this is terrible in terms of code quality. Then, so for 28 line of VHDL, we fall to 9 line of SpinalHDL with a better code expressivity. So yeah, it's good. Then, okay, let's take another example. Let's imagine you have an RGB color input, and you want to calculate the gray level of those inputs by multiplying each of them with a constant coefficient. So yeah, here we can see we have 3 times the same pattern. Basically, you have 3 times signals, unsigned signals, and a floating point constant. And then as output, you get the output of a register. So you have 3 times this pattern. If you want to be smart in VHDL and avoiding rewriting each time 3 times the same stuff, you can define a component which contains that. But you know, using component in VHDL is really boring. It is very verbose, so it's not so good. But here, you can use functions. So let's take the SpinalHDL implementation. So for example, here we can define a RGB value. Then you can define a function which takes as argument hardware unsigned value with elaboration time floating point constant. And this function will return you the output of this flip-flop. So you can see, for example, defining intermediate register has a reg of 8 bits, then doing some fixed point calculation, and yeah, returning it. And then reusing this function multiple times. So yeah, in VHDL and Verilog, you have functions, you have procedure, you have task, but you can't instantiate in those functions arbitrary hardware. You are still kind of stuck with a syntax that will limit you to give relationship between inputs and outputs by a purely combinatorial way, which is not very powerful. Then, yeah, let's take another example. Let's imagine you have a handshake bus, so a very simple bus with just a valid as master arbitration and a ready from slave to say, stop, I'm not ready. Or, yeah, you can go, I'm ready. And a payload. So, as you can see here. And imagine you have two instances of this bus, like source and sink, and you want to insert a queue between those buses. If you want to do that in VHDL, you will have to write all this boring stuff. So, like redefining all signals one by one of your handshake bus. 2 times, then you will have also to instantiate the FIFO, which is, yeah, it is boring. I mean, you have to map, for example, into a single logic vector, all those guys one by one. So here we just have 3 elements, but I work in a company where, in average, we have like 20 signals each time to map into those data structures. So yeah, it's not very great. Then here there is a first approach of how you can do that in SpinalHDL. So in SpinalHDL, a handshake bus is named stream. So a stream is a handshake bus that can carry an arbitrary data type, and here it is an RGB color with this parameterization. So here can define source and sink, which are stream of RGB color of this parameterization. Then you can define a FIFO, like a stream FIFO, which will carry this kind of data type with this depth. And here, you don't have to bind each signals one by one. You even don't need to bind things. Basically, you can directly access I/O of this FIFO by saying FIFO.io.push, for example, to access this pair, or pop to access this pair. And here, for example, it's saying, I want to take my source stream, and I want to connect it by using a fully asynchronous way, so direct connections in respect of signal's direction, to the FIFO IO push port. And then here you say, I take the FIFO IO pop port, and I want to connect it to my sink. So first of all, from 29 line of VHDL to 7 line of SpinalHDL, it is good, but it could be better. Later we will see a better way. Then, okay. So here we've seen that we have an RGB data structure. It comes from the SpinalHDL library. And there is how it is defined. Like it is a case class, which is a case class named RGB, with this parameterization for the construction of it. This class extends bundle. Bundle represents the notion of data structure in hardware. Then here you can define elements that you have in this data structure. So it is simple syntax. And for example, here is the definition of the stream concept in SpinalHDL. So this is still a case class, which takes as construction parameter data type. Then it extends a bundle. It still represents a data structure with the concept of master-slave, because you can take the stream and say it is a master part of my component or a slave part of my component. Then you can define the valid, the ready has Boolean signals. Then the payload as an instance of this parameterizable data type. Then you can implement the asMaster function to say how this data structure could be set as a master or as a slave of a component by saying as output you have the valid and the payload, as input you have the ready. And then you can already do this kind of syntax. And here comes the fun stuff. So basically, I told you before that SpinalHDL is basically a scalar library, which means here, this is object-oriented stuff, which means you can add function in this class, like adding the combinatorial operator connection, and the reverse one, which means the reverse of this one. And you can also, for example, add in this buses definition a function that will, when you call it on a stream, it will instantiate a FIFO, connect this stream on the one you are calling it, connect it to the push port of this FIFO, and then returning the pop port of this FIFO. And there you go. You are moving from this code as before, which do everything by hand in SpinalHDL, to this code, which is only 2 lines, like where you say, I have a source and a sink, which are a stream of RGB color with this parameterization. Then I take my source. I want to queue it with a FIFO, a 16 element, and then I want to connect the output port of this FIFO to my sink. And yeah, here we start to rise the level of abstraction where going out of this mess of wire, which is hardware description things. So this is a simple example. And there is many other funny things that you can do with streams. Like, for example, imagine you want to do this arbitrary hardware. Like, you have a stream of color. Then you want to drop transaction of this stream of color when they are black by adding this arbitration. And then you want to add a pipelining stages for performance reasons, to cut combinatorial paths, or I don't know. If you want to do that, if you want to do that in VHDL, I don't know, it is really boring. And if you want to do that in SpinalHDL, it's only 2 lines. Like you say, I have a stream of RGB color named source. Then you say, I take the source, and I want to throw its transaction when the source payload is black. And then I want to add a pipelining stages at the end of it. And then I will name the return of this staging function sync. So all this stuff here is inferred by just this line. So because, for example, here in the RGB data structure, we also define a isBlack function and this kind of things. So it could look like magic, but in fact, it is pure RTL, because if you look like how is implemented the throw-in function, you will fall on something which is pure RTL. I mean, SpinalHDL is not about adding magic things that will make abstraction for you. You can always look inside how it is done by using regular RTL, like the throw-in function, where you can see it's instantiate a return stream of the same data type. Then by default, it will connect this stream to the return stream, but it will infer those gates there on the valid and on the ready by adding some additional conditions, like if I want to throw transactions, then put the valid to false, and then I will put the ready to true. I mean, yeah, this is still regular RTL. So yeah, now I will change the topic. Safety first. I mean, when you do RTL, it's very easy to do bad things like inferring combinatorial loops across multiple modules, inferring, for example, some latches by forgetting assigning combinatorial signals in all cases. And SpinalHDL will check all those crap things for you. So, for example, this loop will be detected by SpinalHDL compiler, or here the result is not assigned by default if count is false, which will infer a latch. So, which means if you successfully generate, if SpinalHDL generates you the output RTL, you have much more trust in this generated RTL than in a handwritten one, because many, many things are already checked for you. There is also some checks about clock domain crossing, which is done. Then basic abstraction. So yeah, it is a simple example of how you can what could be abstract. Like, imagine you need to do a communication module and you need a timeout inside it to check some things. You can say, I want to create a timeout named timeout, which is a timeout which will tick after 1,000 cycles. And then you can say, if my timeout tick, then I want to clear it. So, but it is hardware. But as you can see here, we are using a function to access our hardware. In place of saying timeout.counter equals 0, I use a function named clear to infer it. Another example is if you want a counter which will count from 0 to 9, you can say I want a counter of 10 states, then you can say I want to clear it, I want to increment it, I want to get its value, I want to get its next value, I want to know if it will overflow this cycle, I want to check if it's equal to 5. I mean, these kind of things, you can kind of have them with VHDL and Verilog, but by using components, and you know how components are boring to use. And here, you just say you want it, and then you can use what you want. Then, oh yeah, because those abstractions are built on the top of SpinalHDL. It's not something integrated in its compiler, which means you can create those abstractions. You can define what is a timeout or these kind of things. So yeah, functional programming. Basically, yeah, functional programming is something which is big. And here it's just one part of it, an example of just one part of it. Like, if you want to infer this hardware, where you have an address, an array of addresses, then you want to check which addresses are equal to a given k, and then you want to know if one of them is true. So you want to do that. You can say, I want to define address, which is a vector of this data type 4 times. Then you can define the k, and then you can say, I take my array of addresses, and I want to create a new array from it. So you use the concept of mapping, and you give as a transformation function that you want to use to translate those elements one by one to the next array. Or you can also use the reduce concept of functional programming, like let's say, I take the its array, and I want to reduce it to a single element by using this reduction function, which will be used on each element, or each pair of elements 2 by 2 to reduce them until a single one. So it's kind of things that you can use very easily with SpinalHDL. And yeah, this is a funny thing. Like, basically, each time you use SpinalHDL, in fact, you are doing some scalar programming by using SpinalHDL library. And basically, each time you use it, it will build into your computer memory a graph of your design, which means you can also ask how this graph is currently to get some information of it. Imagine you have A and B, which are both values synchronized together, which appear together. Then you have A, which go through calculation pipeline that you don't really know the latency. And then when the result of A come out, you need to add the B value that were present at the same moment than the A were present there. So you have to delay B by the same delay than this pipeline. And basically in VHDL or Verilog to do that, to know how many cycles you have to use to specify for this shift register, you will have to count by hand, maybe. Or you will have to run a simulations to look at the wave and these kind of things, but it's not very nice because if the pipelining latency changes there, you are kind of annoying because you have to change things and maybe you will forget, you will create bugs, yeah. But in SpinalHDL, you can, for example, ask the netlist to give you the latency between this point and this point by using the latency analysis function. And there you go, the latency of this pipeline. And you can instantiate your delay with the right delay. I mean, which makes your design much more elastic, which allow you to modify things there without having to care about this stuff. So, yeah, another example. So this is more about what I mean is meta hardware description. Like stopping doing RTL with each time signals and these kind of things. So imagine you want to define this state machine with 3 states, state E, state B, state C, with some conditions there, like when you enter in the state B, you set a counter to 0. Each cycle you are in B, you increment it, and on exit of it, you want to put a result to true. To do that, to do all this state machine, you can do that in SpinalHDL. So you can use a state machine tool, which is, again, one thing which is implemented on the top of it. It's not implemented into the SpinalHDL compiler. So you can say, I want a new state machine. I want to define state A, B, C. which are states, and A is by entry point. Then you can define some signals and some stuff like that. And then you can say, on state B, on entry, I want to set my counter to 0. When state B is active, I want to increment my counter each cycle, and I want to check if my counter is equal to 4. Then I want to go to state C. And on exit of state B, I want to put my IO result to true. I mean, this is really something to show you that SpinalHDL is not a fixed syntax. You can extend it. You can create new abstractions at the top of it, depending your challenges. It could be really useful. Then let's take another example. Imagine you have designed a timer, a simple timer with a simple tick input, a simple clear input, a limit to say when your timer will become full, an output value which will tell you when the timer is full, and a value to get the current value of the timer. So there is a corresponding implementation of SpinalHDL of this component, like you define a timer with some parameterization, like how many bits you want for it. This class extend component to say, yeah, it is component. Then you can define IO of this component in a new data structure by saying you have ticks, which is our input, clear, which is our input bool, and yeah, simple things. Then you can define counter, you can define some behavioral of your component. And then, okay, you have it, you're happy, and you want to map it into something already existing. You want to, from a memory bus like the APB one, you want to be able to set the IO limit of the timer. You want to be able to define which external ticks signals will be able to make your timer tick, these kind of things. To do that, in VHDL and Verilog, you will probably use some switch statements and these kind of things, but here there is another solution, which is really using object-oriented programming. So basically, there is a tool named Bus Slave Factory, and this tool is abstract, which means it is an abstract class, and it defines functions that will allow you to define the mapping between a memory bus and some register of your design. And there is multiple implementation of these tools, like an APB3 one, an Avalon one, and an Axelite one. And there you go. Okay. So as instance, in our timer component, in the bundle data structure, which define IO, we can add a new function that could be used to say, I want to derive this timer component from a memory bus, so bus slave factory, at a given base address in the mapping of this bus. And you can also specify a list of signals which could be able to make your timer tick. You can also give a list of clear signals to say that they can clear it. And then you can say, I want my bus controller to be able to drive and read the IO limit of my timer at the base address +0. So basically, yeah, here you are saying that the IO limit is a register of this bus slave factory that you can access as address 0, and your bus will be able to read it, but it will also take the control of it. It will be able to drive it. Then you can say you want to be able to set the clear flag of the timer when the bus controller is writing the base address +0. So, I mean, this kind of abstract definition of a register mapping allows you to not care about the bus timings. Like, you don't need to know the APB bus timings or the Avalon bus timing or the AXI for bus timing. You don't have to know how the bus work to create a custom peripheral, which is very interesting because it means this function is abstract. You can use it with an Avalon bus, an APB bus, without having to create kind of bridge by yourself to map into a fixed definition. So, and there you go. There is an example how you can use all that stuff. Imagine you want to create a big timer component with a prescaler, with 132-bit timer, and this kind of things. So you can define, for example, an APB3 bus with this parameterization. Then you can define some signals. Then you can say, I want a prescaler of 16 bits. I want a timer A of 32 bits. I want a timer B and C of 16 bits. Then you say you want to create a APB3 bus slave factory, which will be able to map the APB3 bus defined there to some hardware. And then you can say, for example, I take my timer C. I want to be able to drive I/O of this timer C with my bus controller at this address in the mapping. And there is a list of signals that could be able to make it tick. And there is a list of signals that could be able to make it clear. So, yeah, it is very short. I mean, it is really, it is really expressive. You say, I want that, I want that, I want that. I want to connect them like this way. And this is done for you. You don't have to play with wire by hand and adding logic by hand and all these things. It is very flexible. And if you want to edit it, you can't introduce a bug inside it. I mean, you don't have to play with timings. You don't have to play with all those things. Then, yeah, it is a project which was made with SpinalHDL, which is kind of little microcontroller with a RISC-V CPU, with instruction cache, with multiplication, division, extension, and these kind of things, with a JTAG tape to debug it by using by using breakpoint and things like that. There is a SDRAM controller for external memory. There is on-chip RAM. There is an AXI for crossbar to connect all those guys together with a good bandwidth. There is an APB3 bridge to go to peripherals, which are a GPIO, timer, UART, or VGA controller. And basically, there is some things which are interesting is the implementation of this design. As instance, the APB decoder. So, for example, to instantiate this guy, so it is used, for example, 5 lines. So, but I've already talked about these kind of things before. But for example, to instantiate this guy and create all those connections between them, and also to define the mapping of all those guys in this arbitration. This is used that, like you say, I want an APB3 decoder. The master is a APB bridge IO APB, so this guy. And there you can give a list of slaves, like the UART controller IO APB will be mapped at this address with this memory range. Then another example is how this thing is made. So the AXI for crossbar, which connect all those guys together. So here it uses build a pattern from object-oriented world. So basically you can say, I want to create an AXI for crossbar factory. And then you will kind of feed a data model in this tool to say what you want. And when you have feed this tool with what you want, you say, it's all right, you can build yourself, and the tool will do what you want. Then, as an example, in this tool here, we feed the list of slaves, like saying, I have the RAM, I have the SDRAM, I have an APB bridge mapped at those locations. Then you can say, there is, for example, VGA controller, which should be able to access the SDRAM controller IO EXE, and this kind of things. And yeah, it's nearly as easy than to use Vivado things or QSys things, but it's still pure code. It's without using graphical GUI. Then, yeah, about Scala. Basically, yeah, Scala is probably a very good general purpose language. Then, if you want to test it, there is already some Scala IDE which can help you, like to have syntax error highlighting, refactoring, these kind of things, navigation tools which are very useful. There is also a Emacs plugin, and yeah. So about SpinalHDL, it is, as I said, completely open source. You can find some online documentation there. There is some ready-to-use project with some directive how you can install tools and these kind of things. So yeah, if you want to try it, SpinalHDL really go there. There is also some communication channel if you have questions, like a Git chat, do not hesitate to make Git issue if the compiler has some strange things. It could happen, but it is pretty stable now. And if you want to talk to me in private, there is my email address there. So, thank you.
Thank you very much. We have some time left for questions and answers. If you want to leave the room now, that's okay, but please be quiet and take some trash with you if possible. In order to ask a question, please line up at any of the microphones and I will call you out. Yes, please.
Hello, thanks for your talk. I was wondering, so now we have this very high-level description of our hardware. So what is the debugging story like? So if something goes wrong, do I have to look at the VHDL code, or is there some kind of high-level debugging mode that I can use?
Okay, so for instance, okay, I can take an example. So, for example, here, if you have a problem in this drive from function, like register mapping is not working correctly, so in the generated VHDL, you will still keep hierarchy of components and names that you use. Like, for example, this timer here will take those names, things like that. Or here, the logic used, the logic defined there. If you define a signal, for example, in this function, the name will be kept because this function returns an area which, so it's not very difficult. So, because yeah, it still keeps name, and although there is something, it is the fact that, if you use this kind of abstraction there, like throw my transaction when something happened and please add a pipeline stages, because those functions were already verified by somebody else, and you don't have to rewrite it each time by hand. You can kind of type what you think, and it already works from directly, because you are using a more abstract way to define the hardware. You have much less bugs coming in your description. And really, sometimes it's really unbelievable. Like, when you are doing VHDL and Verilog, it never works the first time. But by using those approach, really, sometimes it happens. Already, sometimes it is surprising, but yeah. Then you can take a look in the generated VHDL if you are really not sure and there is something strange. So the generated VHDL is not crap. It is readable. If you search about your signal name, you will find it. It will still keep the same. If you use one statement, you will still retry them in the generated VHDL. So it is not a mess. It is all right. But normally you don't have to go in the VHDL. You will still have points where you can probe signals, and that should be all right.
Thank you.
Question in the front.
Hello. Nice Vortrag. Ever heard of system-level design languages like System C or Spec C, because they do a very similar approach to the problem of raising the level of the level. Ever heard of them?
So yeah, I have heard about System C and the other one.
Spec C.
Yeah, Spec C. I don't know about Spec C. I don't know about it. So about System C, so you can use, I know that you can use many features, or like all features that you want when you are using System C for simulation things. But then for synthesizable things, I'm really not sure that you can use all crazy features of System C. But I'm not an expert. I don't want to say crap, but I think with System C, when you want to come back to synthesis things, you will have to use a synthesizable subset, which is much more restricted and maybe not so much powerful. But maybe I'm saying some crap.
No, you don't, but it's similar to VHDL. Some things you only can use while simulating the whole process.
You are still using sensitivity list and this kind of things, right? Yeah, and
but you don't have to use sensitivity list. You can also use FIFOs for the whole communication, or you can introduce some buses. Very common to your approach, which I really like. So raising the level of abstraction to make everything easier, so you don't just have to synthesize it down.
Okay, thanks a lot.
Thanks.
We're taking the next question from the very back.
Can you compare it to Chisel, which is also Scala-based and also a high-level synthesis tool?
Yeah, okay. So basically, before starting SpinalHDL, I was using Chisel. But I moved away from Chisel because of some bad feelings that I had. So I don't want to hurt Chisel. But there is really many features that are not working well in it. Like, for example, you don't have the possibility. Yeah, you can't use kind of multi-clock domain support, but not really. It didn't work very well when I used it. And for example, you are still forced to use, for example, synchronous reset, which are active high, these kind of things. I mean, Chisel, the team behind Chisel, from my opinion, focus on their needs. They are not seeing Chisel like a tools to solve problems of everybody. Since they have what they want, they don't go further. They don't polish it enough, from my point of view. And really now with SpinalHDL, I'm really much more happy with it because, yeah, I have a page of my documentation which is talking about difference between Chisel and SpinalHDL, and there is really a lot of little things, little issue with Chisel, but which will completely break Chisel if you really want to use it in a productive environment. And about the synthesis, you mean? You have a question about synthesis, right?
No, I just mentioned it was HSL tool. But speaking of the differences, wouldn't it make more sense to just fix Chisel to address those differences instead of forking it?
Oh, I tried to, yeah, okay. In the first time, I started SpinalHDL to understand how Chisel could work behind the scene and then come back to Chisel and fix it. But yeah, it really appeared very fast that it wasn't patchable at all. I submit some fixes and my Git pull were remaining on where they are without any interaction with the team, no feedback. So it was a development process issue, maybe from the Chisel team. But
Thanks.
I tried, I tried.
All right. Next question from the front, please.
Yeah, I think we all know the concept of IP cores with the standard HDLs we have. And how did you think about a review process of the library that is building with Spinal? And how could that happen? So you say you don't want to rewrite code every time, so we have to reuse it. And how can we review it that it's good code?
Yeah, this is, okay, basically, this is probably the next announcement that I really have to do on SpinalHDL. It is really something critical and complicated because when you have done something in the library which come on the top of SpinalHDL, normally you don't have to go back and remove features that you have added. So until now, what is documented on the online documentation could be interpreted like safe. Like using stream to do things is safe because I really put many attention in it. But yeah, there is some work to do on the additional library, which comes directly with SpinalHDL. And it will be one future way of exploration. Until now, we're really focused on SpinalHDL things, on the core SpinalHDL, and yeah, the library is the next step to go further.
you.
Okay, next question from the front, please.
Is it possible with SpinalHDL to create clockless logic or actually asynchronous logic?
Clockless logic, like you mean?
So you don't have a fixed clock. So there's a handshake everywhere between every logic.
Yeah. Like all the logic, everything. There is absolutely no clock, no flip-flop, everywhere in your design. So no, sorry.
Yeah, I also wanted to ask you about another tool. Can you talk about the relation between your system and BlueSpec that's based on Haskell and has been fairly heavily taken up by MIT and worked rather well on things like H.264 decoders?
So I personally, I hear about BlueSpec, but I don't really know about it. I can't really talk about it, sorry.
All right, any other questions? Now is your chance. Do you have any questions from the internet? No. All right, if anything comes to your mind, please find a speaker afterwards. And before you leave, please take the trash out with you. With that, let's give a final round of applause to Charles. Thank you.